Hi everyone, my name is Lydia and this is what I wish that taught me about econometrics and introduction. In the previous video, we saw the trade-offs between using OLS and IV, and we saw that OLS is preferred when X is exogenous because it is more efficient. IV is preferred when endogeneity is present because it remains consistent. And the right choice ultimately depends on specific empirical settings, not a general rule. If you wanted to make also a quick connection with one of the previous video in this little mini arc for IV, you can refer to the video 7 regarding the article of Angrist and Kruger, who found their IV estimate was actually very close to OLS. Now, this was an important finding, not a failure, because OLS and IV basically agreed. And that suggested that OLS was not badly biased in that case. So sometimes the most important result from IV could be that it's not a different estimate, but more like a confirmation that OLS was right all along. And that's a valid and valuable conclusion, okay? So this is also the mature perspective, like IV is at the same time a diagnostic tool as much as an estimation tool. So when OLS and IV agree, you have more confidence in both. But what we're going to see also in this video is a bit of an introduction to the Hausman test, since we're talking about how exactly similar the OLS and the IV results are. The Hausman test provides a sort of a formal answer because it tests whether OLS and IV give estimates that are statistically significantly different, and uses that difference basically as evidence of endogeneity, because if you remember covariance of between X and U, that's really never directly observed. So what's the core idea? When X is exogenous, meaning this covariance is equal to 0, both OLS and IV are consistent, okay? They should give similar estimates, and if different is just the sampling variation. Now, when the covariance between X and U is not 0, meaning my X is endogenous, I know that my OLS is both biased and inconsistent, okay? But IV is consistent, okay? And the difference between them estimates basically the bias in OLS. So what the Hausman test asks is the difference between my beta hat OLS and my beta hat IV too large to be explained by sampling variation alone? Okay, so is this different too large to explain by sampling variation alone? And it's a nice diagnostic idea because you're using the difference between two estimators to detect a problem endogeneity that is otherwise completely unobservable in the data. So in a sense, what the Hausman test is setting for you as a null hypothesis is basically that the covariance between X and U is 0, and your alternative hypothesis that is otherwise, okay, that it's not equal to 0. Now, in the first case, would mean OLS is consistent and differences between OLS and IV are not statistically significant. In the second one, it would mean that these differences are actually too large to be simply associated with the sampling variation. So we are testing whether the gap between these two estimators is statistically meaningful or just noise. There is a Hausman statistic that some of you might recognize, especially if you have worked with software like Stata or R, because it does appear in your results at time, and it's one of the tests that you can very easily apply. So you're going to see that the Hausman test statistic is beta hat IV minus beta hat OLS squared divided by the variance of this difference. Okay? So the numerator is the squared difference between the two estimates, while the denominator scales by the variance of the difference. So under the null hypothesis, these Hausman test statistics, so under the null hypothesis, these should follow a chi-square distribution with degrees of freedom that are equal to the number of endogenous variables tested. Okay, so I'm going to say in here, number endogenous variables. In practice, you never compute this by hand, as I said, so R and Stata do it automatically, but understanding the formula also helps you see what the test is measuring. So as you can see, it's a standardized gap. Standardized gap between the two estimators. To interpret results, usually you look at the p-values. If you've got a large p-value, you fail to reject the null hypothesis. If you've got a small p-value, you reject the null hypothesis. If you're rejecting it, it means OLS and IV are giving you significantly different estimates, and there is evidence of endogeneity, which means IV is preferred, assuming the instrument is valid. Now, note the asymmetry. Rejecting tells you that OLS is problematic. So rejecting, it means OLS problematic. But failing to reject the null hypothesis doesn't prove that actually OLS is valid. And that's a very important key takeaway here, okay? It just means you can't detect a significant difference. With a small sample or a weak instrument, the test may have low power and basically fail to detect endogeneity that is just genuinely present. A practical implementation of this, what you can do is run like the first stage. So you've got X, which is equal to pi 0 plus pi 1 Z plus V. And from here, you save the residuals, okay? Then you include the residuals as an additional regressor in the structural equation. So you would do Y equal to beta 0 plus beta 1x, then let's say delta V hat plus an error term. And what your test is going to do here is literally test whether this delta is equal to 0 or not. So if delta is significantly different from 0, then it means the residuals from the first stage are correlated with the Y. And that's basically your evidence of endogeneity. So if delta statistically significant, that means residuals correlated with Y, which means endogeneity. Sorry about that. Seems we've got that right. So there is one critical caveat, actually. The Hausman test limitation that is often missed is that it compares OLS and IV, but it assumes IV is consistent at that the instrument is valid. So always be very mindful. A significant Hausman test tells you the two estimators disagree, but it can't tell you which one is right. So the Hausman test is a test of endogeneity, but not a test of instrument validity. Test of instrument validity. Okay? So this is why instrument validity always comes first. No statistical test replaces the economic agreement for why the exclusion restriction holds. The Hausman test simply assumes you have already done the work. And again, if you want to do the connection again to the Angers and Kruger example that we've had, keep in mind the Hausman test results in everything by name. The OLS and the IV agreed, so the Hausman test would not reject the null hypothesis, which means that OLS was probably not badly biased in that setting, just education may not have been as endogenous as feared, okay? So once again, the Hausman test formally compares OLS and IV, rejecting when the difference is too large to be sampling variation, but it assumes IV is valid and has low power with weak instruments or small samples. In the next video, we tackle the weak instruments problem directly, what happens when the instrument is valid but not strong enough, and what we can do about it. So stay tuned, and I'll see you in the next video.